We've previously found that that in our max-int problems that we can encounter what we have been calling numerical instability. And roughly the way that we've defined that is when we go to pass our loss function to our numerical optimizer, that different initial values will lead to radically different outcomes or outputs from the algorithm. Now, if that sentence was complete gobbledygook, then you should go back to the previous videos or to the previous sections in the full online course. But nevertheless, we need to contend with this numerical instability. Otherwise, we just don't get a solution to our max-int problems. Now, the previous video showed how we could kind of start to get a handle on potential causes of that instability. And what we did there was that we systematically varied the initial values that we passed to our numerical optimizer, and then studied some things about the outputs and looked for patterns across all of our trials to try to find possible causes for instability if it exists. But that did not fix the instability. It just maybe gave us a window onto possible causes. And now we actually start to take some steps to fix some of that instability. And so this is our first pass, or our first potential remedy. And this is just rescaling data. Okay, so one large, I shouldn't say large because it really depends on the systems that you're working with, but a likely cause of instability can be if your parameters are operating at wildly different scales. Now, the example that we used that demonstrated numerical instability was having constraints on the first, second, third, and fourth moments. Okay. Now remember, a moment is the expected value of a random variable raised to some power, right? So the fourth moment is the expected value of y to the fourth power. Okay. Now that number is going to be, well, potentially, if y is bigger than 1, that number can be much larger than the first moment. Okay, and so all of a sudden we have this data that is, or I shouldn't say data, we have parameters that are working with data of wildly different scales. Okay? And what this can do is cause the larger scale data and parameters to dominate the behavior of the optimizer. Okay. And what that can lead to is a very unstable loss surface, like shown on the top left there, or it's in the center of the slide, I guess. Okay, the yellowish Y there. And so if we transform that data in certain ways, then we can smooth out that loss surface. And the way that we'll try to transform these things is by putting the different parameters onto the same scale. And the dominant or the predominant way that we will discuss doing that is with standardization, but that's not the only way we'll discuss. But we'll briefly allude to one or maybe two others. So with standardization, we subtract the mean and divide by the scale, okay, or standard deviation. So that's shown kind of in the bottom there, underneath the image. And so if you've taken any basic stats course, you're probably familiar with this operation. Okay, and we utilize that operation now to create smoother loss surfaces. So just to kind of make this a little bit more concrete, again, reiterating what the problem is when we have parameters that are operating on wildly different scales. Notice that that y to the fourth can be many orders of magnitude larger than y to the 1 or y to the 2. Okay, and so now in our solution space, moving in the axis represented by y4 is it's hard to attach words to what's going on here without just doing the math. But roughly what's going on is we are traversing space faster, I guess you could say that, and that has a tendency of warping this solution space. Okay, now that's kind of symbolically represented in the image there, right? So we should actually have like 4 axes, and then a vertical axis for loss, right? But we should have one axis for y1, y2, y3, y4, but you can't actually draw that. So so we get what we get here. But it makes the point that if one of the parameters is possibly, if one of the parameters is operating on a much different scale, it can begin to contort the solution space. So, and again, kind of this a contorted solution space is the feature of solution space that leads to slightly different initializations giving wildly different outcomes. Okay, and that is numerical instability. Okay, so this is the thing we want to try to remedy. And so, of course, if we just bring all of the parameters so that they're working on the same scale, then that's what we accomplish. So, so like I said, we will primarily concern ourselves with normalization because it's convenient and familiar. But there's other ways that we can do this, and we'll look at, I think, just one other. But really, any monotonic transformation of our data can potentially do this. Okay. So all that we do is we take y, and so let's say that y represents that left-hand distribution there, right? It's kind of, we'll call it funky. We'll just call it a funky distribution, all right? And then by centering it around the mean and then dividing by the standard deviation, we generate a Gaussian or Gaussian-like distribution that is symmetric. That has a mean of 0 and a scale or standard deviation of 1. Okay, we create a normalized distribution. And so now when we're taking the mean is automatically 0. Okay? The variance is automatically 1. And then any higher order moments are on the same scale as about 0 to 1. It depends on what the, it depends on the data in particular. Okay. So for instance, the third transformed moment here is just the skewness of a random normal variable, and M4 is the kurtosis of a standard normal variable. And so notice what this does to powers of y. Okay, so if y is 1, then after standardizing, if y is 1, then it remains 1 to the second or third or fourth power. If it's less than 1, then it's actually getting slightly smaller each time. And if it's larger than 1, it shouldn't be much larger than 1, but if it is larger than 1, then it's growing, but it's growing at a much slower pace, right? So instead of being orders of magnitude larger, the first moment being orders of magnitude smaller than the largest moment, they are within the same order of magnitude. Okay? And again, this is the thing that smooths the solution space for us. So after we normalize, we just run the maxint procedure on this transformed data, these transformed moments, or on the transformed version of the problem, and that's it. Nothing else changes, and so I'm not showing anything else after this. But it's good to know that that we don't need to stick to the normalized scale. We can convert back to the original scale with a data transformation, and so. Whatever transformation we use, there's a way that we can reverse it or inverse it to get back to the original scale here. All right. So, so for the probability distribution with standardization, this is how we reverse standardization. The large formula up there. Okay. And then to transform the data, so that big one is how we transform the probability. And then to transform the data, then we solve for y from the standardization. Okay, so I hope that you're at least familiar with algebra enough to follow what's being said there. So now, like I said, standardization is not the only process that we can, not the only transformation we can use. Another common one is to use logarithms. Okay, so we can take the log of y, right? And I won't say too much about logarithms. Hopefully you're somewhat familiar with them. But the idea is exactly the same. We transform the data to something that brings all of the scales, to be comparable. Run max int, and then if we want, we can always back transform the probability distribution as well as the data values at the end. Okay, so you can kind of see how to do that on the slide. It's a little bit more detailed on the online course. Okay. All right. So, um, so in conclusion, for this presentation, one of the first things that we might resort to when we encounter numerical instability is to try to transform our data in some way. Standardization is often a good idea, but really any monotonic transformation has a chance of doing this for us. But this does not mean that it necessarily cures all problems, all numerical instability. And so what we will see in the next few videos, I'm not sure how many, are other approaches to taking care of this numerical instability. I believe that the next one will deal with a cause of numerical instability wherein our constraints are very, very similar to one another. They're almost replicating one another. And so this will be a cause of numerical instability. And the way that we will fix that is with a process called orthogonalization. In other words, we will transform not the data, but rather we will transform our constraints in such a way to decouple them. And that will help resolve some numerical instability.